Hello and welcome back to Calculus 1 Exam 3 review for the second time. We already reviewed integration, which is going to be featured on the test because 4.9 is integration, and that is part of chapter 4, right? 4.9. So integration will be on the test. Since definite integral, right, with limits is just one extension of it, we might think about tossing maybe one question that will have limits to compute, which is just upper minus lower, and you're done. So exam will contain these major points. So it's chapter 4, and we have min-max, that was 4.1. You know that you were supposed to take the first derivative, set it equal to 0, and then figure out stuff. The next major point is the first and second derivative test, where the first test will give you increase-decrease, and the second one will give you concavity. We are talking about critical points, we are talking about inflection points, all of those tests. Then we have graphing the function. Graphing the function without calculator, which has that long shopping list, if you remember the 13 things you need to do. Well, those problems are extremely long, and there's a lot of chances for mistakes and things, so I break those points, I break that problem into few problems. I will explain that later. After graphing, we have the word problems for optimization, which is again min-max. So word problems, optimization. We also have linearization. We also have differentials. We also have L'Hopital rule. And finally, I'm skipping over the Newton's method because, you know, calculator. And then finally, integration, which was under the flag of antiderivative. And I will toss in, you know, on this one, the indefinite integrals, which is 4.9, which are those that you have plus c, and definite integrals from 5.2, which is the limits leading into a number as the answer. So these are the contents of the exam. So to go back and talk about what's going to be worked on, we're going to take a look at, so the first three bullet points kind of form a unit because they are all related to, and then the first, right, so all of these connect, and then the first and the fourth also go together. So you know the procedure for min and a max. You have a function, you find the derivative, you set it equal to 0 to find critical points. Those points are either min, max, inflection, and the derivative equal to 0, but also, let me write this, also where derivative does not exist. If you remember, the absolute value function v shape has a point there, And at that point where we actually have a minimum for a function, because it's a spike, you have two different slopes competing, so there's no derivative at that point. But still a minimum. So it's one or the other would give you that. That was an example. Now, first and derivative test, you need to be able to do them entirely from the beginning to the end, which means that you take the first derivative, you find critical points, then you pick test points in between, and then you check for increase decrease. When the test point, when the first derivative of the test point is larger than 0, the function is increasing, or when it's smaller than 0, it's decreasing on that interval. And the same goes for the second derivative test, which means you take the first, then you take the second derivative, set it equal to 0 to find inflection points. Once you have inflection points, you go back and do the same thing like with the first derivative. You pick the test points, and then those test points give you the regions, and then you you test them in the second derivative for concave up and concave down. Which leads us to graphing. So for graphing, you have to find x-intercept, y-intercept, domain, first derivative test, second derivative test, which includes all the derivatives and mean and max and everything else. And then maybe look at the symmetry and look at the asymptotes, horizontal, vertical, slant. There's a whole list of things that you can do to draw the graph. Now that is very time consuming to compute. Since I have a question on min max, since I have a question on first derivative test, second derivative test, I'm inclined to actually give you all of the information as if I already solved the problem, and I'm just giving you to graph by looking at the answers that I got. So I will tell you vertical asymptote is at 7 and the horizontal asymptote is at y equals -1. No slant asymptote. I will tell you that there is no symmetry. I will tell you that the x-intercept is at 5 and the first derivative is positive here and negative there and so on. And you just compile all of that information into a graph. So usually that is what I do. So because otherwise the exam is if you take 45 minutes to do that one problem, there is another 9 problems to deal with, right? So it's not practical. Plus, as I say, it's a double dipping kind of thing because you have the first and second derivative test problems already, min-max problem, which is calculus, and then you have all of the other ones, which are algebra or pre-calc to find asymptotes, to find x and y intercept. That's all. Yeah. Word problems from optimization. We are looking, maybe you want to write it down. We are looking into mainly into the farmer problems. We are looking into some kind of business application, maybe. Those are the most frequent problems because you want to find the maximum volume or the minimum surface area. So there is some of that stuff. Linearization is the tangent line. You should be able to compute, let's say, ln of 3 using linearization by creating the tangent line at E, because E is closest to 3. Now, it doesn't have to be ln, right? ln 3. It could be sine of 5 degrees. It could be sine of 87 degrees, which is close to sine of 90, right? So there's a lot of different things. As long as you know how to compute these, you find the tangent line, you can use linearization. And then we have differentials. Differentials approximate the change, not the value itself, but approximate the change. So now what I have is the way to compute that as well. So that's the differentials. Could be a word problem also. So we'll take a look at some examples when I'm done with the overview. L'Hopital's rule. That one was a long lecture, right? And you remember doing that one problem 3 times for 40 minutes, right? Because it just didn't work out every time I tried. So we have, for L'Hopital rule, you have to remember that the only two indeterminate forms that are recognized by the rule are 0 over 0 and infinity over infinity. Anything else you get, you have to massage somehow into that form first and then use derivatives. So if you have infinity minus infinity, you'll have to do some factoring and then so on. If you have 0 times infinity, you will have to use the trick 1 over f. So you will hopefully review all of that stuff. Going back to the last part, integration. Well, I already did the review today for about an hour and a half of integration when we looked at all of the rules at the beginning of the class. And that lecture is already available for review on the YouTube channel because review of integration, it has its own title. So you can review details of integration where I talked about both indefinite and definite integrals, so plus c or a number. The rest of the stuff from chapter 5, mainly U sub and those formulas like the average formula and so on, that will be there on the final, and we are going to review that one more time after the exam next week. So that's what we have. All right, so let's talk about these things. What I found throughout the years, you are mostly concerned with word problems and then differences between linearization and differentials, word problems for differentials, and then naturally L'Hopital's rule. So those are the kind of top 5 things that freak you out for the exam. Generally, most of the students are okay with the first part because it's procedure, right? The first derivative, second derivative test is the procedures. You either know or you don't. You can't make it up. So let's take a look at some of the optimization word problems. So say there is a river and then you have a rectangular plot of land and you have 2,600 feet of fence and you want to enclose the largest area So what's the largest area that you can enclose? That looks like this. So I have 3 y's and I have 1x. We are going to create 2 equations, a constraint equation and the objective equation. So objective equation is going to be the one that the problem is asking for, and that is largest area, so x times y better than max. This is what we are looking for. Now, constraint. What is the constraint that we have for this particular thing? Well, constraint that we have for this particular thing is that x plus 3y must be using all 2,600 feet of fence. At this point, I solve x equals 2,600 minus 3y. And I plug that into the upper equation. So I have 2,600 minus 3y, which was x, times y equals to a max. That gives me 2,600 minus 3y squared is equal to a max. And now we are ready to differentiate d dy, because the y is the main variable for the time being. That's going to be 2,600 minus 6y equals to, and the derivative of a max is 0. Because that max is the area, which is a number. And then when you differentiate that, you get 0. So what I have is that the 6y is equal to 2600, from where y is equal to 2600 divided by 6, which is approximately what? 24. There will be a 4 there. So let's see. 433.33 repeating. So that is our y. And I can take that y and plug it in for x, because x is equal to 2600 minus 3 times y. So x is equal to 1300 feet. So the dimensions are 1300 by 433.33. Those are the dimensions. So as I said before, these are the farmer problems. They are straightforward. Let's take a look at something else from the book that might be interesting. Oh, I forgot the mean value theorem. I just noticed that. I have to add the mean value theorem. Those problems are easy. Going back to the overview. You know what? I'm going to move this thing higher. And there's the mean value theorem. Can't even tell that it was missing. Mean value theorem has the formula that f prime at some value c is f of b minus f of a divided by b minus a. So it tells us that the instantaneous calculation, right, which is the derivative at some point c, is equivalent to at least one point, right? So if you have a continuity and differentiability conditions holding, then f of b minus f of a divided by b minus a is, I completely lost what I want to say. This is the link between the average value and the instantaneous value, which is derivative. And this c must be between a and b. It only works, obviously, if continuity and differentiability are there. Now, this is the time of the year when I sleep too much and then it's just tired. Usually it's 3, it's also accomplished. Like a bear.
Oh, fuck. Are you 50? Wait, so next week we have the third test and the final is after that?
Yes, next week. So two Saturdays in a row are exams. Next week is M3, following week is the final, and then it's either Calc 1 or 2 in the summer.
The college kids that used to sit there at college.
Used to sit there? Where?
Yeah, the Star Trek fan.
The Star Trek fan.
Yeah, kind of.
He's probably watching, so you're doomed, yeah. Alright. Hi, Star Trek fan. Give him a shout out.
Yeah, I was gonna say, do you actually know really bad with me?
Ah, he's good. Alright, let's do anything else. So pretty much all of these problems are you figuring out two equations. One is the objective equation, the other one is given. So say, I mean, they have such a easy problems like find numbers x and y with a constraint and then maximum product. So find x and y so that product is max given constraint 3x plus y equals 12. So this is like a joke of a problem because everything is spelled out to you. You just need to technically plug stuff in. All right, I'll give you 27 seconds.
No, I mean, that's the respectful amount of sleep. That's 8 hours. Yeah, I know. I only see 5:30 if I stay up that way. Yeah. Is it weird that like when I like drink alcohol, I wake up a lot earlier than I would if I wasn't?
You don't drink alcohol,
I usually dehydration does that. Like I'll wake up. So do I though. At 5 o'clock. And I'll probably be going to bed at like 1 o'clock. You wake up thirsty? No, not really. I usually drink a lot of amount of water to stay too. So I don't really get a headache. I don't get a hangover. Yeah, I haven't had a hangover. Yeah, I don't get a hangover until at least like my mouth becomes like a desert. And just drink gratuitous amount of water. Maybe that's a good study idea, just drink a lot. No. I'm telling you, drinking and derivatives, it works. There's no downside. You get the headache before you. We're metagaming our lives right now. I mean, is that the trade-off, man? What? You drinking and driving, you get the headache before you black out? Or? I don't get headache. Yeah. I don't black out, so.
I guess you're done with this problem because
Yeah, we've been done. You said 27 seconds.
I think I said 18, but it's okay.
Yeah.
X equals 2,
Yeah.
y equals 6.
Max area is 12.
Damn.
Yeah. You sure about that? Yeah. Positive.
So xy needs to be max.
What about the
And then we have that y is equal to 12 minus 3x. We plug that in. So x times 12 minus 3x equals a max. That's 12x minus 3x squared equals a max. Then we differentiate in terms of x and we get 12 minus 6x equals to 0, from where x is clearly 2. And then y is definitely 6. I mean, that's obvious. That's what I said. Please fix it.
You ever going to ask a question like that, but not specify the largest number, but the number of greatest magnitude?
Which is the same.
Well, not like, I think you'd have a different result if you had negatives in there, but like overall the product would be negative itself.
No, the product is always positive. Area is always positive value. Distance is always positive value.
Well, I mean, would you ever, like if you rephrase that, instead of asking for the largest product between the two, and just ask for like the number farthest away from the 0.
It wouldn't change. If you put absolute value, it doesn't change.
Really?
Yep. Let's take a look at differential word problems because that freaks you out sometimes, and mean value theorem. So first, linearization. So linear approximation, what do we have? I'm looking at these problems over here. They're asking me to find the square root of 146. So clearly f of x is root x. And what's the magic value a? What's the magic value a? No. 144, which would give you 12 when you compute. So you are linearizing this at 144 because that's the closest square root right number, the square rootable number to 146. Now you can either do the entire procedure for tangent line, or you can, if you memorize the formula for linearization, you can use that. And I will use the formula for linearization. So L of x is equal to f of a, which is 12, plus now the derivative, f prime is 1 over 2 root x, so it's 1 over 2 root a, that's a 12, so 1 over 24 times x minus a is 144. Half of 12 is 6, right? So L of x is equal to 12 plus x over 24 minus 6. So L of x is equal to 1 over 24x plus 6. That's the tangent line. And now all I need to do is to go and say L. So f of 146 is approximately the same as L of 146, which is 1 over 24 times 1 over 46 plus 6. And now you can, yeah, well, you know, this is designed for calculations by hand. but we're still going to use the calculator real quick. So the answer is 12.0833 repeating forever. Now if you are to take the square root, let's see, of 146, so calculator, square root of 146 is 12.083046, and if you look at our number is 33333, so it gets to be 3/10,000ths off. That's how good this method is. So whether you memorize the formula or you found the tangent line, once you get that line, you compute the original number from the problem. So you first use the number to find whatever is the closest perfect number you can compute with our calculator, and then after that you do the rest. So linearization approximates the number, where differentials approximate the change in the number. So you know that delta y is y2 minus y1. So delta y is approximated by dy. And you know that dy is equal to f prime of x dx, where the dx is the same as delta x. So that's just a little bit of the refresher of what it means theoretically. And now you can figure out the problem. Let's see. Well, actually, I can do the same problem with the square root, but I will find the change and then. So here, the square root of 146, I still have that f of x is equal to root x. I still have that f prime is equal to 1 over 2 root x. And I still have a and 144. So as you can see, everything is the same. Except now, we are trying to figure out the change. So I want to see the change from 144 to 146. So that will be delta x is 146 minus 144, which is 2. So what do I have? I have that the dy is equal to f prime of x delta x, or dx. I call it dx, which is further equal to, we have f prime, so it's like 1 over 2 square root of 144, everything times 2. So this whole thing works out to be 1 over 12. So the change in y is approximated by dy, which is 1 over 12. So how much is square root of 146? Square root of 146 is equal to square root of 144 plus this change. That's how much it is. So square root of 144 is 12 plus 1 over 12. And you can use abacus to figure that one out. right? Repeat it. You get the same. And you know what, well, I should put the air quotes, exact is, right? It's not exact. Now, what are the cool problems for these? Cool problems for these are the word problems where you have approximate change. So I can come up literally with anything. Say you have a melting ice cube, all right? So melting ice cube. Approximate the change in volume if the side goes from 1 inch to 0.85 inches. I just do inch. Approximate the change of volume. What's the volume of the cube? Anyone? My gun.
I was gonna say, dude, that's fair.
Volume of the cube is? Yeah, x cubed. And the side goes from 1 inch to 0.85. So the change in volume dV is going to be 3x squared, which is the derivative, times delta x. But from here we see that delta x is equal to negative 0.15, right? Getting smaller. What happened? Yeah. Me neither, but such is life. So change in volume is approximated by dV, which is 3 times 1 squared times negative 0.15, which altogether works out to be negative 0.45. Ta-da! That's it. So that's the approximate change. Now you can calculate the real change by computing x cubed, right? So it's 1 cubed minus, right, a, and then subtracting those numbers. But we see that there's a negative there. I should have said inches cubed over here because that's the units. That's 2 points off for me. So we see that the number is negative, and the negative number means what? It's getting smaller. Very good. It's melting ice cube. So yeah, right? Awesome. So all of that work together. Another thing that you don't like would be, or don't remember, would be the mean value theorem. Those problems are extremely easy, but for some reason you usually get stuck on those. The formula is, if I mentioned, f prime of c is f of b minus f of a divided by b minus a. You remember, hopefully in class, me drawing those cop traps, right? The road traps.
Oh, the speed trap.
Speed traps, there we go. I couldn't remember the word speed. Because I usually drive without paying attention. So here is the question. Let's say 22. It says find C in interval 1 to 3 for f of x equals to x plus 1 over x. All right, so we have f of b, b is 3. So f of b, that will be 3 plus 1/3 minus f of a, which is 1 plus 1 over 1, divided by 3 minus 1, should be equal to the derivative, which is 1 minus 1 over x squared, but that x is c, because we are computing stuff now. So that's 3 and 1/3, that's 10/3, minus 2 divided by 2 equals to 1 minus 1 over c squared. And you just compute. That's all it is. You can cancel the 2. You get 5/3 minus 1. And then you have minus 1 from the left is equal to negative 1 over c squared. So that's 3/3, 2/3, negative 1/3 is equal to negative 1 over c squared. Multiply by negative 1, and then you just have c squared is equal to 3. So plus minus root 3. But then you only keep the positive root 3 because you are on interval 1 to 3. Negative root 3, which you should also include, you can't include it because it's not in the interval 1 to 3. Now, how do you know this problem is definitely wrong? You solve the problem, you get c equals to 7. 7 is not between 1 and 3. So calculations somewhere went horribly, horribly wrong. So on the derivative side, you will find the derivative in respect to x, and you will plug in c because that's the number you're looking for. So each x will be replaced by c. And on the other side, with f of b minus f of a, just do whatever you learned in Calculus 1, right? Just plug values in for the function and compute. That's the mean value theorem. So, you guys have any questions, concerns? Yes, Neil?
Okay. So going back to the 3x plus y equals 12 and the maximization of the product, right?
3x.
It's like the first part of the idea.
This one?
Yeah.
Yeah. What's up?
So if you just solve for, like, if you don't solve it all, you can just say, like, I want y to be equal to 3, right? It forces x to be negative 5. And then 3 times negative 5 is negative 15, which is a greater absolute value than 12. But is that like an imaginary solution, or?
Depends on how the problem is stated. Probably they're asking for positive values for x and y.
But if there isn't restriction on...
Absolute value will help.
Oh.
You put absolute values. So when you solve with those, it opens up the domain. Like you had the absolute value. Remember how you had the absolute value? So you know that the derivative of ln x is 1 over x. No absolute values anywhere. But integral of 1 over x dx is giving you ln absolute x plus c. So the issue why you have these absolute values is related to what you're talking about, which is the domain. Because domains don't match. ln x function has on the real domain just the positive branch. And 1 over x has both negative and positive, right? And they both have a vertical asymptote at 0. So if you are starting from ln x and then going into a function with a bigger domain, that's never an issue because you can't use negative numbers to begin with, so you will not be using them. You could, but you will not because they were not in the domain to begin with. So you can't pose this ln x problem with negative numbers floating around if you're working on a real domain. But look for integration. Your input function has both positive and negative numbers, right? And if you don't put the absolute value here, you can't use negatives, right? Because the domain, so now when you put in absolute value, your domain looks like this now. So now you can use positive and negative numbers. So this is the part of mathematical analysis of these things that you learn in advanced calculus and so on, to these issues of domain and why exactly each formula does what it does and how it does it, and proofs for all of them. So advanced calculus, which would be usually 300 level, they should have two, like 300 and 400 level courses. So yeah. All right, guys. Well, I will see you next Saturday for exam 3 and then review and then and stuff. Right? Quizzes start tomorrow 6 a.m. Yes. Yes. Very good. Starting tomorrow 6 a.m.
The final submission date for the homework is
Final exam.